Stars, the building blocks of galaxies, live for millions and billions of years. They are born from clouds of gas and dust, igniting nuclear fusion in their cores. This process releases immense energy, allowing stars to shine brightly and support life on surrounding planets. But even stars have a lifespan. Over time, they exhaust their nuclear fuel, leading to dramatic changes in their structure and behavior. When a star much bigger than our Sun runs out of fuel, it collapses under its own gravity. This collapse is a violent process, causing the star to implode and then rebound. This collapse creates a massive explosion called a supernova. The explosion is so bright that it can outshine entire galaxies for a short period. The core of the star, however, survives the explosion. This remnant is incredibly dense and compact. This core, crushed under immense pressure, transforms into an incredibly dense object called a neutron star. Neutron stars are so dense that a sugar cube-sized amount of their material would weigh about 1 billion tons on Earth. Imagine squeezing the mass of our entire Sun into a sphere the size of a city. This unimaginable density gives neutron stars their unique properties. Neutron stars are incredibly hot and spin rapidly, sometimes hundreds of times per second. This rapid rotation is a result of the conservation of angular momentum from the original star. They emit powerful beams of radiation, making them visible as pulsars, like cosmic lighthouses blinking in the vastness of space. These beams sweep across the sky, and when they point towards Earth, we can detect them with our telescopes. Neutron stars are the densest objects in the universe, except for black holes. These fascinating remnants of supernova explosions are incredibly compact, with a mass greater than that of our Sun, but squeezed into a sphere only about 20 kilometers in diameter. Imagine taking a teaspoonful of neutron star material. It would weigh billions of tons. To put that into perspective, it's like trying to lift a mountain with a spoon. This extreme density arises because the protons and electrons in the star's core are squeezed together to form neutrons. This process, known as neutronization, results in a core composed almost entirely of neutrons, packed tightly together. The gravity on a neutron star is mind-bogglingly strong. It's so intense that it warps space-time around it, creating a gravitational field millions of times stronger than Earth's. It is millions of times stronger than the gravity on Earth. This immense gravitational force means that anything that gets too close to a neutron star would be pulled in with incredible force. If you could stand on the surface of a neutron star, which you couldn't because it's so hot, the temperature on the surface can reach up to 1,000,000 degrees Celsius. You would be instantly crushed by its immense gravitational pull. The force would be so great that it would compress your body into a thin layer of subatomic particles. Neutron stars often exist in binary systems, orbiting each other in a cosmic dance. As they orbit, they emit gravitational waves, ripples in the fabric of space-time. These waves carry away energy, causing the stars to spiral closer together. Eventually, the two neutron stars collide in a cataclysmic event. The collision is so powerful that it releases more energy in a split second than our Sun will emit over its entire lifetime. Section 4. Fireworks in space, explosions of energy and matter. The collision of neutron stars creates a spectacular explosion called a kilonova. This explosion is 1,000 times brighter than a typical supernova and releases a burst of light across the electromagnetic spectrum, from gamma rays to radio waves. Kilonovae are also responsible for creating some of the heaviest elements in the universe, such as gold, platinum, and uranium. These elements are scattered into space, enriching the interstellar medium and eventually becoming part of new stars and planets. Section 5. Ripples in spacetime detecting neutron star mergers. Scientists can detect neutron star mergers by observing the gravitational waves and electromagnetic radiation they produce. These cosmic collisions send ripples through spacetime, which can be picked up by highly sensitive instruments like LIGO and Virgo. In 2017, astronomers made history by detecting both gravitational waves and light from the same neutron star merger event. This groundbreaking discovery was a monumental step forward in multi-messenger astronomy, allowing scientists to study the universe in unprecedented ways. These observations provided crucial evidence for our understanding of gravity, the origin of heavy elements, and the nature of neutron stars themselves. By analyzing the data from these events, researchers can gain insights into the extreme conditions that exist in the universe. The study of neutron star mergers is a fascinating frontier in astronomy, promising to unlock even more secrets of the cosmos in the years to come. As technology advances, we can expect to detect more of these events, each one bringing us closer to understanding the fundamental workings of the universe.